So, this is the experimental setup of NMR spectrometer. So, you can see here it is written NMR spectrometer. So, in this experiment, as I told that you need sample to put in the permanent magnet between in the constant magnetic field produced by a permanent magnet, and the Helmholtz coil, to a pair of Helmholtz coil will be attached with this permanent magnet, from where AC field will be modulated with the permanent magnetic field, constant magnetic field. So, here you see this is our sample, is a basically copper sulphate, it is the copper sulphate solution. So, this nucleus of this copper have here spin half. Okay. So, this sample is used. Now, this we have to put here. You can see these two, you see this side this is one magnet and this other side this another this is a permanent magnet basically. So, it is not like pole pieces or something. So, there is a gap between these two magnetic material. So, this sample, and inside probably you cannot see there is a Helmholtz coil, as well as there is a tank circuit from the oscilloscope. Okay, this is the this frequency, from here the frequency. Okay, so this frequency meter basically it is generating this it's the RF oscillation, and that RF oscillation we will put from here this tank circuit. Inside there is a induction coil, and this sample when we are putting that, we are putting at the center of this permanent magnet, and at the center of the permanent magnet in both sides there is a two oscilloscope, two Helmholtz coil, and this induction coil, whatever we are, this is the part of the oscillator. So, it is called tank circuit. So, this tank circuit this way, okay, this is basically here oscillator is here. So, this tank circuit, that inductor, so that I have to connect with this. So, I will connect here. Okay. So, one has to do slightly carefully, yes, I am doing. Yes. So, now these are oscillators. A part of that oscillator is the tank circuit. Tank circuit is nothing but the induction coils are there. So, this induction coil at the center of this permanent magnet, and with permanent magnet the Helmholtz coil are attached, a pair of Helmholtz coil are attached. So, now my sample is in the induction coil or in tank circuit and also in magnetic field. Okay. So, this sample now it is seeing this permanent magnetic field. Now, it has nuclear magnetic moment. Okay. The sample have this, it is a nuclear magnetic moment, it is the equivalent to a single proton moment. Okay. So, now this energy level, because of this permanent magnet, I have not put any Helmholtz coil. current or it is there. So, before applying this Helmholtz coil current or after applying Helmholtz coil current, so this energy level are splitted because of this permanent magnetic field is splitted. Now, with this Helmholtz coil, the splitting just because of variation of the slight magnetic field from the Helmholtz coil. So, this splitting just it will slightly it will vary, okay, it will vary. So, so now if I put this radiation from this oscillator, okay, so in the induction coil basically so that radiation reach to the sample by the induction coil, actually it send this AC signal and it produce the in magnetic there due to this AC signal there will be current, and because of that current there will be magnetic field, okay, because this is the coil magnetic field. So, that field is applied in the perpendicular direction of this original field, okay. So, if this field is in this direction or this field is in this direction, other one will be in this direction. So, we are not talking, so that is why we tell this radiation field, electromagnetic radiation, better if we should tell this radiation field, RF radiation field. Anyway, so now this from RF oscillator, the radiation are going to the sample. Now, what will happen? So, energy level, so there will be, so this system, this sample will absorb the radiation and it will jump from lower energy level to the upper energy level, okay. So, when it will jump, so it will absorb the energy, and this, when it will absorb, when this gap exactly equal to the energy gap, exactly equal to the radiation energy h nu, okay. Now, this gap is varying, so only this absorption will happen in a one complete cycle. This absorption will happen when this gap is equal to the h nu, okay. So, that absorption of the energy, it is basically taking the energy from this oscillator circuit, and this oscillator circuit have this detector and amplifier which will detect this absorption frequency, okay, and it will convert to a signal. Instead of dip, the signal will show peak, okay. So, that is the some mechanism is used to convert this dip to the peak, okay. So, here now let me show so here what we have used, this frequency. So, from here this radiation we are giving to the, so here written y, so this radiation part it is going to the oscilloscope at one channel or y, okay, in xy mode y, and here is basically this CRO x from here. So, this it's a signal for magnetic field, this Helmholtz coil, this whatever current we are using. So, that current, that signal their phase, we can adjust using this, we can adjust using this one, not this one, and the current we can vary using this one. So, this magnetic field information we are giving to the CRO another channel or in X. Okay. So, these two it is there. Now, what is the frequency that we can read from here? Here whatever this switch is there, it is on. Where is the switch? This one. Okay. So, I have switch on. Here you can see, since system is ready for the measurement. So, we have to note down that this current I have applied this 105 milliampere. Okay. So, corresponding this magnetic field will be produced from the Helmholtz coil. So, this magnetic field is very small magnetic field, AC field. Now, this field is modulated with the permanent magnet. Okay. Now, sample is there. Now, here whatever you are seeing 18.74 megahertz, that is the frequency of the radiation generated from the oscillator. It is going to the sample. Now, sample absorb this radiation in resonance condition, and we will get two peak. Here you can see we are getting, so one can use phase shifter. Okay. So, instead you can see, instead of here in ESR we got 4 peaks, but here we are getting 2 peaks. Similar arrangement, why 2 peaks not 4, that I explained you. Okay. Now, what we have to do? We have to make coincidence of these 2 peaks, just varying the phase. Okay. What is the phase? Phase between this here, these 2 signals are going in, one is in X and another is Y. So, one of them, this phase we are changing. So, then these 2 will coincide. So, that I am doing. So, just I am changing to get it coincidence. Okay. So, now it is coincidence. So, one has to do nicely tune the things, and as I told, this coincidence one, it should display at the middle, at the middle of the display. So, it is almost at the middle of the display, but if it is not in the middle of display, slightly you should play with this frequency. Where frequency? Here, this frequency, okay, of the oscillator. So, it is very sensitive. You can see it is very sensitive when I am touching it. You see, when I am just touching it, it is fluctuating. So, slightly I would like to take slightly this side. So, let me, you see, just it has gone. So, very, you see, it shifted. Okay. So, frequency are different. So, it is telling when it will display at the middle, then that frequency one can take as a resonance frequency. So, high F2. So, I think this way I can show you. Yes, I am shifting. Yeah, now it is at middle, you know. Okay. So, now you have to note down this frequency 18.74 megahertz. So, only I need this frequency, and magnetic field, basically what is the magnetic field for permanent magnet? It is around 500 Gauss. So, in calculation we will take this 500 Gauss. Now, this then you can calculate, if you know the frequency, then you calculate G factor. Okay. So, this you can repeat this experiment, just changing, if I change the magnetic field, what happens? Just check. It will be just, I think, if I change the magnetic field, okay, it changes. Okay. So, what we will do? We will just use phase shift to make them coincidence. make them coincidence, okay, to make them coincidence. Now, to bring it at the center of the display, so I have to use this frequency change, I think. So, it is very sensitive, it is, I have to, yes, no, other side, yes, it is at the center of the display. So, now it is 18.72, okay. It is 18.72, so not much variation. Now, you can understand that their field we are changing, Helmholtz coil current we change to 33, but there is no much change of this frequency because as I told that field is really negligibly small compared to the field of permanent magnet. Okay. So, this way just one should do this experiment, take 3-4 sets of data and you will get this G factors and take the average of this 3-4 from 3-4 set data, whatever G factor you will get, just take average of them and that will be your result of G factor of nuclear G factor. Okay. So, this is a very nice experiment and the principle of this experiment whatever I describe here. So, this same principle is used in research laboratory also for NMR spectroscopy, but here we do not have any temperature variation. Here our magnetic field we cannot vary. Okay. So, we need such arrangement. So, distance between the permanent magnet, if we change, so field can be, you can vary the field. Okay. So, this more options will be attached with the system and more sophisticated electronics will be used to study the relaxation time. So, that is basically spin lattice interaction one can study from the NMR. So, that way it is a very good experiment for teaching lab which will help you to understand the principle not only for this measurement of your sample, but for research also one can study various kind of samples for various characterization. So, here one parameter G factor we are reporting, but lot many things can be done. We have one NMR in our research lab. So, there are many others characterization also we do, but here our intention is to introduce the spectrometers, so that in future one can use this instrument in research laboratory confidently. So, I will stop here. Thank you.